Number one. The force between two bodies having identical electric charges. This references the Coulomb's law, where you can actually measure the forces between two charged particles. In our case, we're talking about two individual atoms, actually ions, right? Because Coulomb's law only works for ionic compounds. So if you have two positives, for instance, then those are going to be repulsive forces, right? There's no bond going to form there. Or two negatives, same thing. What we're interested in is a negative and a positive. Except that the question says the charges are identical, right? So we have repulsive forces. That's a force. We're talking about these two at the top, right? Those are repulsive forces. And we can measure the magnitude of that force. All we need is Coulomb's law and whatever his constant is. And we have a magnitude of charge here and a magnitude of charge there and the distance between them. And that'll give us the force. Okay, number two. I'm gonna leave that there just in case. Or if it gets in the way, then I'll have to erase it. Atoms having equal or nearly equal electronegativities are expected to form what? Well, if you look at the answers, we're looking at a certain type of bond. So if they have equal or nearly equal electronegativities, are they going to form ionic compounds? No, they have to be covalent compounds. The only way they can bond is through sharing electrons, because nobody's wins. Equal electronegativities. But even if they form covalent bonds, there's not enough difference in electronegativity between them to make the bond polar. So that means the bond has to be nonpolar. And the one that satisfies those conditions is C, nonpolar covalent bond. All right, scroll a little bit. We can get two in here. 3. For the elements cesium, fluorine, and chlorine. Cesium, fluorine, chlorine. Oh, we'll erase this. What's the question? The order of increasing electronegativity. So which is the most electronegative out of that group? Remember? Using the Pauling scale. Lower left to upper right, increasing. Upper right is fluorine. All right? So the most electronegative is fluorine. Okay, what's the least electronegative? Whenever I have a triplet like this, and you have to order them, I find out which one's the top and which one's the bottom, and then put the other one in the middle. So what's the least? Lower left? That would be cesium, wouldn't it? That means chlorine is in the middle. Cesium, chlorine, and fluorine. Okay. Proceed. Number 4. The electron pair in the CF bond. could be considered. Okay, we're talking about that bond between carbon and fluorine. We're not saying it's in any particular molecule. We're just saying for that particular bond, looking at the answers, well, there are several answers. The electron pair could be considered what? Closer to carbon or closer to fluorine? They're closer to fluorine. The dipole moment is this direction. So this one's going to have a slightly negative and this one's going to have a slightly positive. We know that because fluorine is the most electronegative and everybody else is less. So A can't be it. Electrons can't be closer to carbon because fluorine is more electronegative. So which one? Well, C's out also, so maybe B. Closer to fluorine because fluorine has a higher electronegativity than carbon. There's your answer. They're not centrally located because they're not equal. That would be, E would be counted out also. I think I'm doing a lot of them. Yeah. We'll get all of them to begin with, and then when we start getting some repeats, we'll skip. Number 5. Which of the following molecules has no dipole moment? Okay. We're talking about molecules here. What do you need to know to determine the dipole moment of a molecule? You need to know 2 things. The electronegativity of the bonds and the geometry of the molecule. If all of the bonds are nonpolar, then the whole molecule is nonpolar. Now, might have to consider lone pair electrons too. But if they are polar, the molecule is still not polar unless the geometry is correct. Okay. So which of the following molecule has no dipole moment? Well, let's look at it. How about A, carbon dioxide? Do we have a difference in carbon and oxygen? Yeah. Yeah. Those are polar bonds. Now we need to know something about the geometry. So how do we do the geometry of a molecule? First thing, Lewis dot structure. So carbon has 4 valence electrons, oxygen has 6. Well, there are 2 of them. Right. So that's 16 valence electrons. All right. Then you draw your structure with carbon in the middle, oxygen on the end. So that's 4 electrons subtracted equals 12 left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we used up all our electrons, but we still don't have an octet on carbon. So how do we get an octet on carbon? Well, 2 possibilities. You could take a pair from here and a pair from here and make a triple bond on that side, but that would be unbalanced. And we talked about formal charge too, didn't we? I think we did. If you calculate the formal charge of that one with a triple here and a single there, it would be radically unbalanced. But if you just take 1 from either side and make a double bond, now it's perfectly balanced. And the VSEPR model says that 2 groups around the carbon means what? It's linear, right? 180 degrees bond angle. So the dipole moment this way and the dipole moment that way cancel each other out. We found our nonpolar molecule. Since we have D says all of them, we probably have to do at least 2. Right. But we know that this one is nonpolar. How about B? If B is polar, then, well, E can't be right because we found a nonpolar. Then if B is polar, then D can't be it, right? And then C can't be it either by process of elimination. So how about ammonia? How do we do the dot structure on ammonia? Well, nitrogen has 5 valence electrons. How do I know that? Count from the left. How many groups over? 1, 2, 3, 4, 5. 5 valence electrons for nitrogen, 3 for hydrogen means 8 total. So we have a nitrogen, we have a hydrogen, hydrogen, hydrogen. That's 6 electrons, 2 electrons left over. They have to go on the nitrogen. So what is the electronic structure for this molecule? 4 groups, tetrahedron. Okay. So the tetrahedron is going to look like this with a triangular bottom. Nitrogen's in the middle somewhere, and then there. So we're going to have maybe a lone pair here. We're going to have hydrogen in the back, hydrogen here, and a hydrogen here. Now that's the geometric shape that we're working off of, but the bonds themselves are between the hydrogen and the nitrogen, here, here, and here, which means what shape do we have as a molecule? A trigonal pyramid, right? That's a trigonal pyramid. All right, so, and the electronegativity of nitrogen is less than hydrogen, so it's going to be this direction. 3 ways, and since those bonds are not on the same plane, since they're bent a little bit, then they're going to give us a vector added dipole moment that's like this, plus that lone pair. All right, so that is a polar molecule. All right, so we found our answer. A is the answer. It is the only non-polar one in there. And we know water is a polar molecule. We've done that one several times. All right, water is going to be oxygen, 2 hydrogens, and 2 lone pairs right here. Actually, water is a very polar molecule. There he is. Let me see. I didn't give you guys something to sign in on. All right. Where did it go? I'll just go ahead and mark Sam zoomed and everybody else present. Take care of that. Okay. So the answer to that one is A. Carbon dioxide is the only nonpolar molecule in that group. Six, next page. Yeah. There we go. We get 6 and 7. Which of the following has the smallest radius? Okay. We did periodic trends for neutral atoms. That was not a problem. When we're talking about ions, though, if you go from a neutral atom to a negative ion, an anion, you're going to increase the radius of that species. If you lose an electron, you're going to decrease the radius of that species. But I think this one warrants a different approach. Notice what we've got here. Potassium, chlorine, rubidium, sulfur, and argon. So what comes to mind for me is isoelectronic series. Are those isoelectronic? All right, we've got argon as 18 protons, and 18 electrons still because it's neutral. What if we go to the left of argon? That's chlorine, right? Okay. What if we go to the left of that? There's sulfur, which has 16. So all the negatives, let's go to the right. If we go from argon down to the next period over on the far left side, you find potassium. There we go. And we've also got rubidium. And rubidium is not in that series. Rubidium is in the 5th period, below potassium. So it has 37. Okay. Now, if we're trying to put these in order, rubidium is going to be the biggest one, without a doubt, because it's in the next higher principal quantum number. I mean, it's way out there. So we have to order these. Oh, which has the smallest radius? Okay. So rubidium. Yeah, it won't be rubidium. It's got too many electrons. Even though it has more protons, it's still got so many extra electrons in another energy shell that it's going to be too big. So it can't be this one. So we got to look at these. Right? They're all isoelectronic. They have the same electronic structure. And that would be, let's see, 18. 1s2, 2s2, 2p6, 3s2, 3p6, probably. 2, 4, 10, 18. Yeah. They all have that structure electronically. Now, if they have the same electronic structure, what's the difference? The difference is the number of protons. If they have the same electronic structure and the most protons, that most protons would shrink that electron cloud down to the smallest size. That makes potassium the best candidate. Potassium ion is the best candidate for the smallest ion. And if you look it up, I mean, just use a reference manual and look at the radius, you'll find that that potassium ion is smaller than the rest of them. Okay. All righty. Number 7. Which of the following arrangements is in order of decreasing size? Okay. 7. Decreasing size. So what do we have here? We've got gallium 3+. Taking the inventory of what we've got available. Calcium 2+, potassium, chlorine, and sulfur ions. Okay, B has sulfur, chlorine, potassium, calcium, gallium, all those. Okay. Gallium, sulfur. Okay, they all have the same. So we've got them all up here. We just have to put them in order. Order of decreasing size. Now, do we have a situation here where we do have isoelectronic series? There's sulfur, then chlorine, skip argon, go down to potassium. These are all isoelectronic. Right. Calcium has 20 and 19 and 17 and 16. Okay. So the troublemaker is going to be gallium. We got to figure out what to do with gallium because it's got 31 protons. But the order here should be the smallest radius of this group should be the one with the most protons. So in order of decreasing size, so we know that calcium is going to be here, then potassium, then chlorine, than sulfur. Okay, we get smaller and smaller and smaller. Now the trick is, where does gallium go? Gallium is has the same valence shells as calcium, but it also has d orbitals. Right? Because we've gone all the way across from calcium to gallium, we have to cross over that whole list of d orbital fillings to get there. The thing is that even though you have those Ds, these do have 31 protons. So I'm willing to put gallium on this end as the smallest ion of the bunch. And I think if we check, let me see. Did I put that in the review document? I mean, in the work problems? Yeah. So I checked it to confirm. Wait a minute. In order of decreasing size. Okay. This one has them in order of increasing size, but the smallest one is gallium 3+. Any problems? No? Okay. That was 7, 8, 8 and 9. In the reaction between magnesium and sulfur, the magnesium atoms what? Become anions, become cations, become part of polyatomics, share electrons, crystallize. I think crystallize was just thrown in there because they didn't have a clue what to put for E. Share electrons, no. Not between a non-metal and a metal. That can't be. Doesn't become part of a polyatomic ion because polyatomics are covalently bound. Right? So polyatomics are always non-metals. They form covalent bonds to form that ion. So it's either A or B. So in the reaction with magnesium and sulfur, the magnesium atoms, metals tend to lose electrons, which means they become cations. Right? They want to become cations. Most nonmetals have higher electronegativity than metals. How about 9? Choose the molecule with the strongest bond. Okay, this one is somewhat counterintuitive. If we look at the series, these are all halogens, right? And all the halogens are diatomic. We learned that first in both classes, actually. All the halogens are diatomic. So we've got this one, we've got this one, got bromine and iodine, right? Yep. They're not all equal. Notice as you go down, the size of the atoms becomes larger. Okay, so they're bonding with similar orbitals, but they're not bonding with the same orbitals. And the closer that you can get those atoms together, the more overlap of their orbitals you can get. Right? If they're farther apart and you're using bigger orbitals, then you don't get the overlap that you need to strengthen the bond. So this is the weakest one. And you get stronger to this one. You get stronger to that one. The problem arises, we would think that you would get stronger there because fluorine is the smallest atom, you get more overlap. The problem is Fluorine is so small, the nuclei can get so close together. Now you got proton repulsion. You get those nuclei so close together that they start to repel each other, and that weakens the bond. So in reality, chlorine has the strongest bond of that group. Okay? I threw that one in there because it was counterintuitive. And by the way, we know that's true because we've measured the strength of the bond. So what we had to do was explain it. If you just try to reason it, then that doesn't make any sense. All right, who's next? We're going to need those. 12. I'm going to run out of time. I just know it. These molecules have a zero net dipole moment. Okay, so we need to know polarity of the bonds and geometry. Let's look at them. Each one of those is going to have polar bonds. I do believe. It's just 4, 5. Yeah. Boron, hydrogen, nitrogen, oxygen, sulfur, fluorine, oxygen. Zero net dipole. Ozone. Okay, ozone might be a problem. Because they're all the same molecule, we wouldn't expect them to have a dipole moment. But look at the answers. We've got A is 3 and 5, B is 1, 3, and 5. So there might be more than one that have zero net dipole. Right? It's pretty sure, I'm pretty sure that I would expect ozone to have a net dipole, not have a net dipole. Let's just do them. Okay. Boron trihydride. Right. Boron has 3 electrons. Hydrogen has 3. So that's 6. So we have boron, hydrogens. That's it. They're all used up. That's one compound where you have less than an octet. All right, you have 3 groups. What's that structure? Trigonal planar. That's nonpolar. How about 2? NO2. NO2. Okay, nitrogen has 5, oxygen has 6 each, so that's 12 and 5 is 17. All right, so we have nitrogen, 2 oxygens, which is -4, 13. Did I do that right? NO2? Yeah, NO2. So we've got 6 there, 6 there, which makes, we have 1 left over. It goes right there. This happens to be a free radical, an unpaired electron. So, but you still count it as a group. So 3 groups is trigonal planar, electronic, and then the molecular structure would be bent. This is polar. That one's nonpolar. All right, what's 3? Sulfur hexafluoride. Sulfur has 6 electrons, and halogens have 7, so that's 42 and 6 is 48. Right, 1, 2, 3, 4, 5, 6. All right, so that's 2, 4, 6, that's 12. If you used up 12, 36. So if we have 6 more around each fluorine, 6 times 6 is 36. We're gone. So this structure with 6 groups is what? Regular geometric shape. Octahedron. There are no lone pairs, so this is also the molecular structure. And this is nonpolar. That is what we're looking for, isn't it? No dipole moment. Yep, nonpolar. So we got this one so far. And let's make room for 4. Roman numeral 4, ozone. Okay, 3 times 6 is 18. So we have that one, and that one. 2, 4, 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the middle oxygen doesn't have an octet yet. So what are we going to do? We're going to say, make a double bond there. There we go. So the central atom has 3 groups, which makes it trigonal planar, electronic, and molecular would be bent. Okay. Now these oxygens all have the same electronegativity, but it's bent, and there's a lone pair up here, so it's going to look like this. Something like that. This lone pair gives that side of the molecule a negative charge. That's why I think this one is polar. That's 4. Yeah. So 1 and 3 are definitely polar. So it's either B or D. So let's look at the last one. Phosphorus pentachloride. So phosphorus is 5, and 7 times 5 for the halogen is 35, so we've got 40 electrons. Phosphorus here, 1, 2, 3, 4, 5. That, so that's 20, which makes 20 electrons left over. 1, 2, 3, 4, 5, 6. 6 times 5 is, I can't do that. Did I miscount? 7 times 5, 35, 40. 2, 4, 6, 8, 10. Oh, 10. We got 30 left over. So 6 times 5 is 30. That uses them all up. If we do octets all around, and phosphorus has exceeded the octet. So what's our regular structure here? 5 groups is a trigonal bipyramid. Okay, that's a regular shape. With polar bonds, they all cancel each other out. So this one is nonpolar. So we have this one, 1, 3, and 5. That's B. Okay. All right, 13. 13. Okay. We're starting to dip our toes in the organic chemistry pond here. 4 carbons linked together. And those numbers are there just to identify which carbon it is. It doesn't mean that there are 4 carbons or 3 carbons or 2 carbons. It's just first, second, third, and fourth. And then we have, I'm going to use this one for a bond. Yeah. Another one here, and then oxygen. Okay. The question is, how many electrons must be shown as bonding or non-bonding electrons in the Lewis structure? This is simple. Just add all the valence electrons up, right? How many hydrogens? 1, 2, 3, 4, 5, 6. Well, I'll tell you what, you can do it. And that would be the best way. Just to take the hydrogens first. 1, 2, 3, 4, 5, 6. 6 electrons for hydrogen. 1, 2, 3, 4 carbons is 4 times 4 is 16. And then 1 oxygen, which should be 6. So that's 12, 28. 28 electrons, which is D. That's how many electrons you have to account for if you're going to draw the Lewis dot structure for this molecule. Let me see, before I erase that, am I going to need it again? Well, 14 uses the same molecule. How many electrons are shared between carbons 2 and 3 of this molecule? Crotonaldehyde. Let's go ahead and do that one since we've got the molecule up here. So we've got 28. We've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We got 8 electrons left over. So we start from the outside and work our way in. 1, that's 6. 2 electrons. Where do the 2 go? Well, if you're looking at forming, and this is 14. If you're looking at forming octets for everything, notice there's an octet here already. 2, 4, 6, 8. There's 2, 4, 6 here, 2, 4, 6 there, 2, 4, 6 there. So how are we going to get? We've got lone pairs here that we can use to fix this carbon, but these 2 carbons are isolated. The only way to work those is to put the 2 electrons on one of these carbons and then use it to make a double bond there. That's an octet. This would be 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so we've got a double bond here, got a double bond there. And the question was, how many electrons are shared between 2 and 3? So between these 2, they share 4 electrons. 2 double bonds. All right. Let me see. All right. We need to do this one. We're going to draw a Lewis dot structure for this ion. If there's a charge on a group, you've got to add that charge into your valence electrons when you count them up. So we've got 3 halogens for 21 plus 1 for the charge equals 22. Okay, 2, 4, 18. That's 12, which is 6 electrons. 1, 2, 3, 4, 5, 6. Okay. How many lone pairs of electrons are around the central iodine atom? We've gone far enough. Lone pairs? Well, we've got an octet here. got an octet there. We've got more than an octet here. And we've got 1, 2, 3 lone pairs. Notice the wording. It says how many lone pairs, which would be 3. All right, 16, 19, and 20. Okay. We can take a shortcut on 19 because it's talking about the resonance structures that we can draw from the molecule O3. We drew O3 already, and we came up with that. 2, 4, 6, 8. We came up with that structure. But remember, we made a double bond on this side. We could make a double bond on the other side. Like that. There. So resonance structures here would be like that. And you can only have 2 resonance structures for ozone, because these are both valid Lewis dot structures, and we can't decide using the valence bond theory. We can't decide which one's which. So that's where resonance comes in. Okay, 20. Which of the following types of molecules always have a dipole moment? Okay, let's see. What do we got to choose from? Well, let's see. Let's take linear with 2 identical bonds. Always has a dipole moment. Linear with 2 identical bonds is nonpolar. Right, so it can't be A. How about B? Tetrahedral molecule, 4 identical bonds equally spaced. No, those all cancel each other out. Right, so it can't be B. How about C? Trigonal pyramid molecule with 3 identical bonds. We just did one a few minutes ago. That one is always dipolar molecule, because of the reason that it's this shape. You don't get a regular shape of a trigonal pyramid out of an electronic structure. This is derived from a tetrahedral, and the only reason it's trigonal pyramid is because you got that lone pair there. So this one is always polar. Well, it always has a dipole moment, let's put it that way. Depends on how big that dipole is as to whether it's polar or not. All right, so we found the answer. Which set contains atoms listed in order of increasing electronegativity? This one should be fairly simple. Let's see. Increasing electronegativity. All right. For A, we have fluorine, nitrogen, carbon, and silicon. Fluorine, nitrogen, carbon, and silicon. Increasing. What's wrong with this picture? That one's on the wrong end. Right? So it can't be A. How about B? Phosphorus, nitrogen, oxygen, fluorine. Phosphorus, nitrogen, oxygen, and fluorine. Phosphorus. Okay, that's right. But are they in the correct order? Well, fluorine, yeah. How about oxygen? It's just to the left of fluorine. Nitrogen's just to the left of oxygen. And then phosphorus is below nitrogen. That's a good order. That's greater than that one, greater than that one, greater than that one. I think we found our answer. Uh, 22. Which choice has the bonds listed in increasing order of increasing bond energy? Oops. Don't write the answer down. Write the number down. 22. Okay. The first one has HF, HCl, HBr. It should be the other way around. The closer you can get the molecules together, especially if they have different electronegativities and one is slightly positive, one slightly negative, HF should be the highest energy. HCl next and HBr. So they're flipped, they're wrong. B is a comparison of single, double, and triple bonds, and those are in the correct order. So B is a good answer. C, we've already talked to that one. Chlorine should be where bromine is. Chlorine has a higher bond energy than bromine. Actually, fluorine has a higher one than bromine too. So C is false. And D is D. This one less than this bond in this molecule. Yeah. And then the carbon-carbon bond in this molecule. All right. The carbon-carbon in this molecule is a double bond, and the one in this one is a single bond. And this one is a triple bond. So they're in the wrong order. They need to be flipped around. All right, so we found our answer, it's B. '23. In the gas phase, which of the following diatomic molecules will be the most polar? Okay. Here, since we don't have numbers, what we have to do is say which ones are farthest apart on the periodic table. And it should be obvious. Cesium is way down in the lower left-hand corner and fluorine's in the upper right-hand corner. That should be the most polar. Cesium fluoride should be the most polar molecule out of all those. We could go through them one by one, but I think probably use too much time doing that. 25. Which of the following ionic compounds has the largest lattice energy? That most stable to most favorable to a stable lattice. Okay, in this one, I might have to put them all up here. Okay, we got barium oxide, beryllium oxide, cesium iodide, sodium bromide, and barium sulfide. Okay. So what is it that draws these ions together? Well, the first thing is the Coulombic forces. Coulombic forces are higher for multiply charged ions. So if we can find barium is a 2+, sulfur is a 2-, they're good candidates. A plus and a minus, plus and a minus. Okay, so these would not be good candidates. They're only single charges. Beryllium, yeah, beryllium is a 2+, 2-, and 2+, 2-. Okay, so we're going to say barium sulfide, beryllium oxide, and barium oxide. Now we're looking at how close can those charges get to each other. All right, so we look at size. Which ones of these are big? Well, barium is huge. And sulfur is bigger than oxygen. So barium sulfide loses to barium oxide. But oxygen may be, well, actually oxygen is pretty small. But beryllium is much smaller than barium. So I would say the lattice energy for that beryllium oxide will be the highest of all those. And that's my reason for it. $25, $26. Okay, this one might take some mental gymnastics. The first electron affinity value for oxygen is what? Unfavorable or favorable. And the second affinity is unfavorable or favorable. Electron affinity. So we have oxygen gas plus an electron yields oxygen minus gas. That's electron affinity. And this one's the first. The second would be this one, gas, bring that down here, plus another electron. O2 minus gas. Okay. This one should be exothermic. It should be favorable. It should give up energy as the electron approaches oxygen because oxygen is fairly electronegative. It will attract electrons. So this one should be exothermic or favorable. But when you try to put another electron on there and you've already got a negative charge, you get repulsive forces now. So the second one should be endothermic or unfavorable. That just means you've got to force the electron in there. Now, that begs the question. We know that oxygen prefers a 2- charge because it completes its outermost orbital, makes it look like neon. But if one is exothermic and the other is endothermic, then why does it end up over here? My explanation is you get so much energy back here that some of it can be used to drive the electron here. So it's the balance. It's not each step, but it's overall the balance that favors 2- charge on oxygen. Okay, so that's D, favorable, unfavorable. All right. 27. Using the following reaction data, calculate the energy of an HF bond. Let me see. I don't want to spin my wheels on this one. All right. So this looks to me like we're going to use Hess's law. In other words, we combine these equations into our target equation, and then that allows us to add up the enthalpies for each one to find the answer to that question. So the first question is, what's the target equation? What's the energy of the HF bond? We're talking here lattice energy, right? The HF bond. I think I'm on the right track. Well, how do we calculate the energy of a bond? We need a diatomic molecule like that. And it has to be in gaseous state. right? Otherwise, we're putting energy into phase changes and all those other things. So the bond itself is formed from this. Right? That's not lattice energy. Forget I said that. That's the target equation. So out of those that we have, HF, do we have HF in there? Yeah, the first one puts HF on this side, but the way it's written, it's on the other side. So we have to flip it. And that means 2HF yields H2 plus F2. Okay, but we only need one of those. So now we're going to have to take half of it. So we've got to change it to 542 positive and divide it by 2. So that gets this one right here with that one. Now that makes, let's see, that makes this one a half and this one a half. And this one is a whole, just one. So the next one, let's take H. Let's do hydrogen. So this one looks like it will give us what we need. Right? With 432. We didn't have to flip that one. But we only need one of these. Right? So just one of those. That means this divided by 2. And then there's one in there also for fluorine. That's the bond energy of fluorine. Now we're going to take half of this one, and half of that one means 1 fluorine. So that's 154 divided by 2. Okay. All right. So if we take a half of that one and a half of that one and a half of that one and add them together, we should get 564 kilojoules per mole. Okay, Hess's law. Now, did we do it right? Well, this half cancels that half fluorine, this half cancels that half hydrogen. There's a hydrogen, there's a fluorine, hydrogen, fluorine. We're good. We got a couple more like this in there. I don't know if we're going to have time to do them, because I've only got a half hour left. All right, 28. Which one of these molecules will probably not exist as a stable molecule? I think the first one is methanol. Yeah. Second one is formaldehyde. This one is, I don't know. This one is probably acetylene. And then this one is, I'm not sure what the name of that one is. Propene. Anyway, in order for it to be a stable molecule, we have to write a valid Lewis dot structure first. So this would be 4 for the hydrogens, 6 for the oxygen, and 4 for the carbon. Right, so that'd be 4, 8, 14. So we have this one, this one, this one, this one, oxygen and hydrogen. Notice that in organic, when we write organic formulas, the hydrogens are bound to the carbon that comes before them. These hydrogens are not bound to that oxygen. the carbon is bound to the oxygen. Carbon is bound to the oxygen, carbon, oxygen. Well, there's hydrogens and hydrogens. Okay, just so you don't misunderstand. All right, so 2, 4, 6, 8, 10. So we need 4 more electrons. 1, 2, 3, 4. That's it. That's a good structure. How about this one? Let's see, 4 plus 2 plus 6 is 12. So carbon, 2 hydrogens, and an oxygen. So 2, 4, 6. 1, 2, 3, 4, 5, 6. That's 12. So carbon needs a pair. Goes in here like this. Yeah, that's a good structure. How about this one? 1 carbon, 3 hydrogens, 1 oxygen is 9, 13. So if we do carbon, 3 hydrogens, and an oxygen, that's 2, 4, 6, 8 is 5. 1, 2, 3, 4, 5. Now do that right. 4, 3, 6, 13. Yep. 2, 4, 6, 8. Yep. 5. Okay. Notice that this is a free radical in the first place. And this carbon is satisfied. But the oxygen is not. And we can't satisfy the oxygen. There's no way. 2, 4, 6, 7. It's only got 7 electrons. Right? This is unstable. Now, it doesn't mean it doesn't exist, but it's very unstable because it's a free radical. It's going to react very quickly. Well, we found our answer. CH3 is not stable. Acetylene, I'll just go ahead and draw this one. There you go. That's very stable. C3 and 4 H's. Let's see. Hydrogen here, hydrogen here, hydrogen there, hydrogen there. It's probably like that. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Let's see. 12 and 4 is 16. 2, 4, 6, 8, 10, 12, 14, 16. That's it. So it has 2 double bonds in the middle. And that's a fairly stable molecule. All righty. Let's see. Do we want to mess with this? And using the following negativities, select from the following group molecules that fit the given statement. The molecule contains a carbon atom with trigonal planar geometry. All right. You actually don't need those electronegativities. Which one of those would give a trigonal planar carbon? Remember, you can have more than one center of symmetry in a molecule. And the first one is a good illustration. This one, let's see, 29. So A has this carbon bound to another carbon, which has a hydrogen and an oxygen. So we have 2, 4, 6, 8, 10, 12 electrons used up, and we have 4, 8, and 6 is 14, 15, 16, 17, 18. So we have 18. That means we have 6 electrons left. 1, 2, 3, 4, 5, 6. There's an octet. This one just needs that pair to make an octet. So which one has trigonal planar symmetry? Well, look, you got 1, 2, 3 groups around that carbon. 3 is trigonal planar. So A is a good answer. And since E says none, then we found our answer. We know carbon dioxide is linear. We've done that one before. Methyl chloride, CH3Cl, has 3 hydrogens and 1 chlorine around. That's tetrahedral. And C2H6 is like this. So those are both tetrahedral. We found our answer. It's A. Let's see. Of the following, which molecule has the largest bond angle? 34. What are the possible bond angles that we've studied so far? Linear molecules have 180 degrees. There's nothing bigger than that. So if we found a linear one in here, I think we got our answer, don't you? We looked at ozone earlier, right? Ozone had this shape to it, right? So its bond angle would be about 120 degrees. OF2, and we haven't done that one yet. So that's 7 7's 14 and 6 is 20. So O and F would be 2, 4, 16. 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. And then there. So that would be a bent molecule because our electronic structure is 4 groups, tetrahedral. That's a bent molecule. And a bent has, well, a tetrahedral has 109.5 degree bond angle. So it's even smaller than this one. How about C? HCN. Do you remember doing that one in class? 1, 4, 5. So that's 10 electrons. Hydrogen, carbon, nitrogen. Right? 2, 4, 6, 8, 10. So we got to have, carbon has to have an octet. So we take 2 from here and 2 from here. Right, that. And that makes a triple bond. That's linear. 180 degrees. So C is our answer. More than one have equally larger bond angles? No, because water is derived from tetrahedral is 109.5. So the 180 degrees for hydrogen cyanide is the answer. Which of the following molecules is nonpolar overall? Okay, I'm going to skip that one. Which of the following molecules are non-linear? Maybe we'll come back to that one. Molecular structure. Okay, what I would caution here is that whenever you draw the Lewis dot structure for an ion, be sure and consider the charge. If it's a 1 negative charge, you have to add an electron. It's a 1 positive charge, you have to subtract 1 from your valence total. Then you can go with drawing your structure. And these are kind of busy work, so I'm going to skip those for now. There's another one. And be sure and read the question. Does it ask for electronic geometry or molecular geometry? If it's molecular, then you draw the electronic and then you cover up, use your hand, cover up the lone pairs and say what's left over. That's your molecular geometry. All right, we'll have to come back to that one too. How about 50? Use the bond energies given below to calculate the enthalpy change for the reaction. So the reaction is HCN plus H2 yields CH3 NH2. Now, how are we going to figure out the bond energies? Remember what we do. We just take the, add up the energies for each of the bonds in our reactants and subtract the bond energies for the products. But this doesn't tell you what kind of bonds you have. You got to draw the structures. We just drew hydrogen cyanide. Right. Hydrogen's easy, right? This one has 3 hydrogen bonds, a nitrogen, and 2 hydrogens, and a lone pair. Now, if you don't draw the Lewis dot structure, you don't know it has that lone pair in there. Okay, now we can do how many, well, there's a carbon-hydrogen bond here. Carbon-hydrogen, 413 kilojoules. And then we have a carbon-nitrogen triple bond, 891 kilojoules. And then we have one hydrogen-hydrogen bond, 432. Okay. Then we subtract the total of these bonds. So we have 3 carbon-hydrogen bonds, 413 each. And then we have a carbon-nitrogen single bond, 305. And then we have 2 nitrogen-hydrogen bonds, 391. Okay? That's the thinking part. The rest is crunching numbers. And if we crunch the numbers correctly, we should end up with minus 158 kilojoules. Okay? All right, let's see. Given the following information, okay, this is another Hess's law operation. And I've got another one similar to it, but it's more cryptic. This one. I think this one would be more valuable. 52. All right, our target equation. Calculate the lattice energy for rubidium chloride. So you have to know how to write the lattice energy equation. The lattice energy takes the gaseous ion of the cation plus the gaseous ion of the anion and makes the solid out of them. So rubidium chloride, we got Rb plus gas, and we check it, rubidium. Yes, it's an alkaline metal, has 1 charge. Plus the chloride, and that yields rubidium chloride solid. That's our target equation. Now, the cryptic part of this question has to do with the given information, the given reactions. If you don't know what they mean, then you can't write the reaction that will help you build a Hess's law compilation of the equations. So the first one, well, that's fairly simple. Rubidium solid to rubidium gas. Right? I don't need to go over that one. That takes 85.8 kilojoules per mole, right, to turn a solid into a gas. That's a sublimation energy. IE1 for rubidium. IE1 for rubidium is the ionization energy. Remember how you write that one? Rubidium gas yields rubidium ion gas plus an electron. Okay, that's what IE1 means. BE means bond energy. The bond energy of chlorine, right? It should be a gas. Yes, it will have to be a gas. And then what you end up with is 2 chlorine atoms. And that's so much energy, 397.5. Excuse me, 226. HF, delta HF, that's the enthalpy of formation, the heat of formation of rubidium chloride. Remember how to write that one? You start with the product, rubidium chloride solid. And then you work your way back. What's the abbreviation there? Delta HF. Yeah, that's right. And you work from the most stable form at room temperature and 1 atmosphere pressure. So the dichlorine molecule gas is where you start from this one. And then the rubidium solid metal. This one's okay. Got one of those, one of those. This one, though, you need a half. So that will give you minus 431 kilojoules. That's exothermic. And then EA. What is EA? Oh, electron affinity. Electron affinity of chlorine is chlorine gas plus an electron yields chloride gas. There you go. So all the energies that go into those are given here in that format. So now how do we solve this problem? Well, I would just tackle it one at a time. Where do we have a rubidium plus gas? Right there. But it needs to be on this side. So we got to write it backwards. Plus an electron yields that. Right? So we reversed it, but we didn't take a fraction or a whole number multiple. So all we have to do is change the sign. Oh, I left one out. This one. There we go. So we could use either one of those, actually. No, we can't, because we need the ion. Excuse me. My mistake. Okay, so we reverse the sign on this one, which should be ionization energy minus 397.5 kilojoules. Okay, so that takes care of this one. There it is right there. Okay, how about the chloride? Where's the chloride? Chloride's here, electron affinity. It's on the wrong side. So we got to write chloride yields chlorine gas. And this is plus an electron. Now we flipped that one, which means we need plus 332 kilojoules. Okay, we got this one and this one done. All right. How about rubidium chloride solid? Here it is. And it's on the correct side. So if we write this one in here, rubidium solid plus half of a chlorine molecule yields rubidium chloride solid. Okay, I went too far on that. Let me back it up some. Okay, the energy for that one is as given. Heats of formation, minus 431. Okay, so now we got this one done. Right there. Okay, the rest of it is going to be getting rid of these terms that don't exist. Electrons are already gone. That one's on the left-hand side, that one's on the right-hand side. So we're good there. Okay. How do we get rid of rubidium gas? Well, I would say two birds with one stone. That rubidium solid to rubidium gas is sublimation. We need deposition. We need to flip it around. So that puts the gas on this side to cancel that one, and the solid on that side to cancel this one. So if we write it this way, gas yields solid. What's the value for that one? Negative 85.8. Now we got rid of this one and this one. Okay, what do we got left? We've got chlorine, atomic chlorine gas, and 1/2 of chlorine molecule. So it looks to me like maybe bond energy would work. So this one's on the left-hand side. That one's on the left-hand side. Need to flip it. So we need to put 2 chlorine atom gas and there. Okay, so got them on the correct side. This one should cancel that one, except this one needs to be 1/2. So we need to say 1/2 of that would give us 1 chlorine atom, which would cancel this one, and would give us 1/2 chlorine molecule, cancel that. Okay, but we need to, we flipped it, didn't we? Yeah, we flipped it and changed the sign on bond energy. 226. So it's minus 226 divided by 2. There we go. Now we just add those up. That's a lot of work, isn't it? We should get minus 695. Kilojoules per mole for this reaction. Now, is that reasonable? Well, yeah. Lattice energies are fairly high. That's a big number, 695 kilojoules. Plus, they're exothermic with a negative sign. So yeah, it's reasonable. Now, the one we skipped right before it, you would use a similar way. Number 50 maybe, or 51. You would use a similar way, but for that one, the equations are actually written out for you, so you don't have to interpret. That's why I skipped to this one, because the way the information is given to you, if you don't know how to interpret it, then you're stuck. Okay, I got 10 minutes. 53. Beryllium chloride, excuse me, in spite of larger electronegativity differences between bonded atoms, beryllium chloride, between bonded atoms in the beryllium chloride molecule this molecule has no dipole, while sulfur dichloride does have a dipole. So how do we explain that? Beryllium chloride versus sulfur dichloride. All right, if we draw the Lewis dot structure, this has 7 each, which is 14, and beryllium is 3, so that's 17 electrons. Sulfur has 6, plus 14 is 20. Okay, so if we draw the structure, that's 2, 4, minus 4 equals 13. Is that correct? Beryllium chloride. 14 plus, 2, excuse me. 16. 2 plus 14 is 16, minus 4 is 12. Okay, so we got 12 left over. There they are. This is a linear molecule. So the dipoles cancel out. This is nonpolar. How about this one? Sulfur, chlorine, chlorine. So we have 2, 4, 16. 2, 4, 6, 8, 10, 12 equals 4. This is going to be a tetrahedral electronic structure or a bent molecular structure. So we're going to have dipoles that way on the bonds, but since it's bent, right, the dipole is going to be a vector addition of the dipoles gives you the dipole toward the chloride side. That's why this one is polar and that one is nonpolar. You just have to put it in words. Okay, one more. I think I can get this one done. And then we can do a lab. 54. ICl4 minus. Okay, we got 5 halogens, which means 5 times 7 is 35, plus 1, 36 electrons. Okay, iodine is going to be in the middle. Chloride, 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 chloride. Okay, 2, 4, 6, 8. 28. Octets all around for the chlorines. Right, that's 4 times 6 is 24. And that's 4 left over. Got 2 there, 2 there. And the Lewis dot structure is not complete until you do that. If you don't put that charge over the brackets, then it's not valid because it doesn't have enough electrons to justify that arrangement. Now, what's the structure? Well, it's got 1, 2, 3, 4, 5, 6 members, which means octahedral electronic geometry. So if we draw the octahedral, where are they going to go? Well, iodine's in the middle, and the chlorines are going to be around the square, in the planar square. And the lone pairs are going to be at the apexes. That's just the way octahedrons like it. That means that the molecular structure is square planar. Right? And even though chlorine is has a dipole moment, this molecule has a dipole moment on bonds toward the chlorines, they all cancel one another out. Right? So it's nonpolar. That's it, I think. Except for the ones I skipped, and I think you can probably get those. If you have any trouble, the review document talks about all those shapes that we were. In fact, it's a good idea to go through and get those shapes, learn those shapes, because if you, those take a lot of practice to get a feel for 2 groups, 3 groups, 4 groups, 5 groups, and 6 groups. And then what do you do? What do you get if you've got lone pairs in there? That just takes a lot of practice. So it's not something that I can really make you any better with in just a few minutes. Okay, any questions?